we had this working a second ago, so if it doesn't work now, something's cursed.
Right.
Is that okay? Can you see that?
Good for me.
Yep, great. Okay, well, thank you very much for the invitation, and thank you everyone for coming. This is yeah, I'm looking forward to this. So first of all, a disclaimer. So I wrote the abstract thinking that would be a good topic. When I got around to planning the talk, particularly as this is a sort of introductory theme, I did come to the conclusion it was going to be a bit ambitious. So I have pared things down a little. I'm still hoping to talk about the Bowditch JSJ decomposition, but that's going to come more at the end, and possibly not. I'm not going to state the full theorem. I'm going to focus mostly on the sort of slightly less complicated results that lead up to that. So that's my aim. I'm sorry if I've lured you here under false pretenses, but well, as we were talking about just as people were coming in, a great advantage of Zoom talks is if that happens, if you feel misled, you can just do something else, and I'll never know. So I won't be offended. So I'm also hoping that this can be a bit informal. If you want to interrupt with any questions, that would be great. Any questions or comments or thoughts, or, well, like a lot of people, I fear I have a bit of a tendency to rush through talks with slides. When I'm at a blackboard, that slows me down, but the slides I can just sprint through. So if I'm going to try not to do that, but if I do, please tell me. Please, yeah, ask a question to slow the pace down a bit, or something like that. So, right, I suppose I should first tell you a bit about what I'm about to tell you. So, splittings and boundaries of hyperbolic groups is what I've got written down here as the title. So, splittings, I really mean sort of Bass-Serre theory and cutting things as amalgamated products and HNN extensions. And I'm not going to assume that you already know what all that means. So I'm going to spend the beginning of the talk talking about that. These are sort of topologically motivated ideas. So at least, well, from my point of view, they're topologically motivated ideas. So that's the approach I'm going to take. Then I'm going to, I've been told that this is the first of several talks you're going to have about hyperbolic groups here. So I'm going to tell you what a hyperbolic group is and what the boundary of a hyperbolic group is, and give you some examples. And then I'm going to get onto the main thing that I want to talk about, which is the link between splittings and these boundaries. So the idea is going to be you can somehow see splittings of groups in the boundaries of them, as long as they're hyperbolic. So, right, I'll get on. So splittings first. Oh, I need to. Right. Okay, splittings. So the ways in which you can split a group are sort of really motivated by the ways in which you can split a topological space. I mean, you can cut it into two pieces. That's, I mean, we've all got a fair idea of what it means to cut a space into pieces. It's just exactly what you'd do with, I suppose, a pair of scissors or something. And splittings of groups are motivated by that. So here's a picture of a space which seems to be called, which I've called Z. It's being cut in half by this dotted line, and it's been cut into two pieces called x1 and x2. x1 is the piece on the left, x2 is the piece on the right. And now I've got a piece in the middle, y, which is sort of where x1 and x2 meet. So if x1 and x2 are closed, for example, then y is the intersection of x1 and x2. But anyway, it's sort of the space that it's a common subspace of x1 and x2, so that gluing x1 to x2 along that subspace gives you z. So that's what I mean by a splitting of a space. Either we think of it as you can cut it in half along y, or we think of it as going the opposite direction. You start off with your spaces x1 and x2, and then you glue them together along y to get z. So I just want to be very clear about that. So that's how we split up spaces. And then, of course, this implies something about fundamental groups. If you're cutting up a space like this, then the Ciphertv-Van Kampen theorem tells you what you're doing to the corresponding group. The Ciphertv-Van Kampen theorem, I'm hoping we all know, says that the fundamental group of the space we started with Z is an amalgamated product of the fundamental group of x1 with the fundamental group of x2. And that amalgamated product is taken along the fundamental group of the bit in the middle, y. and then I've written a presentation for exactly what that means. So I1 and I2 are the inclusion maps of Y into X1 and X2. So that's what we think of when we think of splitting a space and the implication at the level of groups. I've wanted to go through this in some detail, even though I'm sure you'll know this is familiar, because then this is actually only one of two things that can happen when you try cutting a space with a pair of scissors. I suppose the clue to that is the title of this slide, Splittings of Spaces, the separable case. Of course, something else can happen, which perhaps people, not topologists, but other people maybe don't think about so much. So on the next slide, the other thing that, yeah, I should say, on groups, this is an amalgamated free product. So on the next slide, we look at the non-separating case. So here again, we're taking a pair of scissors to the space Z, cutting it along Y, but because there was a hole or something in Z, this cut along Y hasn't actually separated the space into two. So in this picture, we cut along Y, that's a dotted line again, and towards the right-hand side of the picture. And now we haven't cut Z into two pieces, it's still only one piece, and that piece is called X. But that piece is sort of simpler because it doesn't contain this loop anymore. So I've labeled on this picture, again, these inclusion maps from Y. Previously, Y included into the two spaces X1 and X2. Now Y includes into X in two different directions. And so I've marked that, and I've also marked a loop T that goes sort of transfers to Y. It goes out of one side of Y, does something in X, and comes back the other side of Y. And using that, it turns out, this is, I suppose, an exercise that you can, again, use the Ciphertv Kampen theorem to write down a presentation for the fundamental group of Z as something involving the fundamental groups of X and Y. I suppose I'll tell you, the trick is, if you haven't done this, well, either there's a version of the Ciphertv Kampen theorem for groupoids instead of groups, or if you're a bit less fancy, you can instead of cutting along Y, consider cutting along Y union that loop that I've labeled T, and then everything works, I think, or something like that. Anyway, the point is, now we no longer get an amalgamated product, we get what's called an HNN extension. So the notation for this is that pi1 of Z is isomorphic to pi1 of X, the fundamental group of X, star, and then the subscript, the star has a subscript pi1 of Y. So we call this the HNN extension of pi1 of X along pi1 of Y. And then I've written a presentation. So this tells us exactly what an HNN extension is. It's the free product of pi1 of X with that loop T that I drew, and then we add some extra relations that tell us that going around T conjugates sort of one side of Y to the other side of Y. So I1 star includes Y into one side of X, and I2 star conjugates Y into the other side of X. And this relation tells us that those two things are the same up to conjugation by T. So this is the second fundamental group operation that, that we're going to use to cut up groups. So when we cut up spaces, I've said either we separate or we don't separate. When we cut up groups, either we amalgamated product or we do an HNN extension. Those are the two cases. So these two slides, the thing I've been trying to do is motivate why these are the two operations we will be talking about. So before I move on, any questions at all? Anything I haven't, you think I should have said, but I didn't? No, I'm not hearing anything. I'm hoping that at some point someone does ask a question, but I'll move on. Oh, and again, so this is called an HNN extension. Okay, now graphs of spaces. Oh dear, I've included the wrong graphic into this picture, so I'm going to have to ask you to imagine something in a sec. Out of these simple cuts, so when we start off with a space, we cut it up I've told you 2 ways you can cut up spaces. This separating and non-separating case. If you apply these over and over again, then you've cut in lots of different places, and you get a decomposition of the space that we record in a graph of spaces, which is what I wanted to show you here, but clearly I've messed up the LaTeX, so sorry about that. So I'm going to describe it, and then you'll have to imagine it, I'm afraid. So a graph of spaces is a graph gamma, just normally a finite graph, but it could be an infinite graph, I suppose, with some extra information attached. So at each vertex of the graph, you get a space, a topological space, gamma v, and at each edge, e, you get a topological space, gamma e. And then that's, if we were looking at a picture, all you'd be seeing is I'd have drawn a small graph and labeled some of the vertices gamma v with the associated spaces gamma v, gamma e. So you're not missing much. And then also, just like how before we needed to record the information of how y includes into x1 and x2, and then later how y includes into x by these maps I1 and I2, the graph should also come with the information of how gamma e includes into gamma e plus and gamma e minus, where e plus and e minus are the 2 endpoints of e. So to say that again, a graph of spaces is a graph gamma with a space at each vertex and each edge, and then for each edge, 2 continuous maps that include gamma e, the space gamma e, into the 2 spaces at the endpoints. And then you can, hopefully you can sort of imagine that given that information, that's sort of enough information to tell you how to glue all the spaces together in a natural sort of way to get the whole space that you were starting with. So this sort of records a way of cutting a space up into pieces. So that's what I mean by a graph of spaces, that information there. So it sort of records a possibly complicated decomposition of spaces, but it's built out of like single separating and non-separating cuts. Graph of groups, oh no, so I must have overwritten a graphic just before I compiled, just at the end. I didn't check this, obviously. So here again, you'd be seeing a picture of a graph, but to be honest, you're not missing much with these images. Analogously, so we can build decompositions of groups by iteratively applying amalgamated products and HNN extensions, and such a decomposition, or sometimes we call it a splitting, is recorded as a graph of groups. So just like a graph of spaces was a graph with a space at each vertex, a graph of groups is a graph with a group at each vertex. So it's a graph at each vertex. You get a group, and at each edge you get another group, and also the edge groups. You get homomorphisms now that include the edge groups into the vertex groups. So an edge group has a group there, and you get 2 monomorphisms that map that that group into the groups that sit at either end of that edge. And okay, I expect maybe I should say a couple of easy examples. So before we had the two simplest splittings we could think of were an amalgamated product and an HNN extension. An amalgamated product corresponds to the graph that is just a single edge. It's got 2 vertices, and we put pi1 of x1 and pi1 of x2 at the vertices, and pi1 of y, that's the label of the edge. And an HNN extension just has 1 vertex and 1 edge that starts and ends at the same vertex. And the vertex is labeled pi1 of x, and the edge is labeled pi1 of y. So, and then the more complicated splittings are just really, you just do multiple amalgamated products and HNN extensions. Everything can be built out of those. Okay, so I think that's everything I was going to say. Oh, yeah, that's everything I was going to say about graphs of groups and graphs of spaces. Might pause again just to ask for any questions, just because I know on Zoom it can be quite hard to interrupt someone.
So in practice, we should think that gamma is just like a finite graph.
Yeah, right. Finite graph is what yeah. So in a way, I suppose it doesn't have to be, but yeah, think gamma is a finite graph. We're only ever going to be making finitely many cuts of these groups or spaces. I think if the groups are finitely generated, then you don't lose anything at all by insisting that gamma be a finite graph. And yeah, for the point of view of this talk, definitely gamma is a finite graph with just some extra labels of groups and things on the edges.
Maybe it's worth saying something about what happens if there's a cycle in the graph.
Yeah, right. So if there's a cycle in the graph, then that sort of means that at some point you're doing an HNN extension. There's some sort of non-separating cut behavior going on there. So if you imagine, for example, the graph that is just a single cycle, so maybe it's got n vertices and n edges connected in a cyclic way, then if you wanted to sort of glue those groups back together, then what you'd do is take one edge at a time. So in each edge corresponds to an amalgamated product. You would work out that amalgamated product and then sort of collapse the edge because you've dealt with that now. You'd keep doing that until you were just in the case where you had a single vertex and a single edge left. And then there's just one final HNN extension to do. So yeah, cycles in the graph correspond to having to do HNN extensions at some point. Yeah, thanks. I think I hope I think that was hopefully helpful. Any other thoughts at all? No, I'm happy to move on. Good. So that describes splittings. Now there's this really, in my opinion, really quite elegant theory of splittings. It may be what I've just described has seemed a bit combinatorial and not very nice and geometric, but there's this really nice theory called Basset theory that tells you that tells you that splittings correspond to group actions on trees, and I want to just take this slide to explain a bit of that idea. So, so graph of groups decompositions, the point is they're going to correspond to actions of that group on a tree. So I'm going to just describe where that idea comes from. So given a graph of groups decomposition of G, you can build a corresponding graph of spaces. So all you do is you, for each of the groups, take some space that has that space as a fundamental group. For example, you could choose the space K, that group one of these classifying space type objects. But anyway, just choose any space that has has the vertex group or the edge group as a fundamental group, and then replace that vertex group or that edge group by the corresponding space. And we've gone from a graph of groups to a graph of spaces. The graph of spaces, well, by gluing everything together, we get one big space, and that space has fundamental group G. Okay, so from a graph of groups decomposition, we arrive at a space whose fundamental group is G, and the space has a graph of spaces structure. Then consider the universal cover of this space X. Well, we can just lift the graph of spaces decomposition of X to a graph of spaces decomposition of the universal cover. Now the underlying graph is a tree because it's got to be simply connected. And in fact, it's going to be an infinite tree because, well, the universal cover is a much bigger thing than the X itself. So the underlying graph of this space X tilde is a tree, and the action of G by deck transformations on X tilde descends to an action of G on T. So I've just described a series of steps that take us from a graph of groups decomposition of G to an action of G on a tree T. Now the theorem of Bass and Serre says that this is really a one-to-one correspondence in a way that I'm not quite going to make precise, that splittings of the group as graphs of groups correspond to actions of G on trees. In fact, we can be a bit more precise. A splitting with underlying graph gamma corresponds to an action on a tree T where the quotient of T by G is gamma. So the if we know the tree and the group action, we can work out what the underlying graph of groups is. And in fact, we can do a bit more. We can work out the group labels that go on the vertices and the edges as well, because for any vertex of the tree, the stabilizer of V, so that's a subgroup of G, is isomorphic to that says G subscript V. It should be gamma subscript V, the group that labels the equivalence class of the vertex V, because V is a vertex of T, so there's an equivalence class of vertices, just the orbit of V under the group action. That corresponds by the previous sentence to a vertex of gamma, and the equivalence class of V is a vertex of gamma, and the group that labels that equivalence class is the stabilizer of the vertex. So maybe that's a little complicated, but that's the story. So there's a one-to-one correspondence between actions of the group on trees and decompositions as graphs of groups of your group, and you can sort of read all of the information of one of those two objects over to the other, and vice versa. So you really can move quite easily between these actions on trees and graphs of groups decompositions. And I'm probably going to do that quite a bit over the rest of the talk. So the moral, is that splittings and actions on trees are equivalent. And at least for me, I suppose I think I'm quite geometrically minded. Actions of groups on trees are easier things to think about than splittings. So I like this theorem. Any questions about this Basset theory before I start talking about hyperbolic groups? Yeah, I will move on then. And yeah, great. Okay, so hyperbolic groups. I've got here the compulsory picture that all talks about hyperbolic groups contain. So first of all, I'm going to tell you what it means for a metric space to be hyperbolic. So a metric space, a geodesic metric space, is hyperbolic if there exists a delta, so that all triangles in the space are delta slim. I should expand on this a little bit. So I'm sure we all know what a metric space is. A geodesic metric space is a metric space where any pair of points can be connected by a sort of shortest path. And that the length of that path is then equal to the distance between the points. So that's what a geodesic is. And the reason why we need geodesics is that's sort of in part of the definition of the word triangle. So triangles are collections of three vertices joined by geodesics. So we need to be in a geodesic metric space for this to make sense. And then what does it mean for a triangle to be delta slim? That's what I've tried to illustrate in this picture. A triangle is delta slim if each of its edges is contained within a distance delta of the union of the other two edges. So looking at the picture, I've drawn these sort of banana-shaped neighborhoods of the left and the right edges, and I've chosen delta so that this triangle is just about delta slim, because we see that those two banana-shaped neighborhoods just about cover the bottom edge. And similarly, we'd want that for the other three choices of edge. So this triangle here is delta slim. And then the space is hyperbolic if there exists delta, so that all triangles are delta slim. So you need a sort of uniformness. And geometrically, that sort of forces triangles to be very, very pointy. They're not allowed very much area because the edges all have to curve inwards towards the middle to make this work. So another way of thinking about this sort of heuristically is that triangles have to have uniformly bounded area, which is something we associate with the hyperbolic plane, for example, but definitely isn't something we associate with Euclidean plane, where triangles can be as big as you like. So that's a delta slim triangle, and yeah, hyperbolic space. A group then is hyperbolic if it acts geometrically on a hyperbolic geodesic metric space. So geometrically, that's an adverb that is being attached to an action. I'll just tell you in words what it means, but I don't want to get bogged down in really technical details or anything. So geometrically means three things. It means firstly, by isometries. So obviously you'd want this, otherwise there was no point really in assuming that the space was a metric space. So the action definitely has to be by isometries. Secondly, it has to be co-compact. So the quotient of the space by the group is a compact space. That sort of tells you that you can get, just by moving around according to the group, you can get basically anywhere in the space. There aren't big regions that you'll never see by just jumping around according to group elements. And the third thing is that it has to be properly discontinuous. So this says that if you've got a compact subset of the metric space, then all but finitely many elements of the group take that compact subset off itself. So that's saying that group elements mostly move things around quite a lot. You don't get lots of group elements sort of concentrating things around one little region of the space. So that's what it means for an action to be a geometric action. And then a group is hyperbolic if it acts geometrically on a hyperbolic geodesic metric space. The sorts of groups you should have in mind here are like finitely presented groups. It turns out that these groups are all finitely presented. So we're not thinking Lie groups or finite groups or anything. We're thinking sort of the groups are going to be infinite discrete objects. So that's hyperbolic groups. Let's think of some examples. I think everyone introduces the same set of examples here, so you've probably seen these before if you've ever thought about hyperbolic groups at all. But first of all, some examples of hyperbolic spaces, I suppose. The most boring example is that any bounded metric space is a hyperbolic metric space, because you can just take delta to be the diameter of the space, and then just trivially all triangles are delta slim. So that's boring. We're not going to really think about that. Now trees, these are the first interesting example. So trees, just including the real line, that is a tree, I suppose. So a tree is actually a space where all triangles are actually zero slim. If you try drawing a tree and drawing a triangle in that space, you find that each of the edges of the triangle is actually contained in the union of the other two edges. You don't even need neighborhoods. Each edge really is contained in the other two. And that's just because in a tree, given two vertices, there's really only one path between them. So trees are hyperbolic with delta equals 0. And sometimes we think of hyperbolic spaces as being spaces that are a bit like trees in some ways. And also the main motivating example, I suppose, of hyperbolic spaces are things like the hyperbolic plane and the higher dimensional analogues of those. Those are hyperbolic with delta equals log of 1 plus root 2, it turns out. That's sort of because in the hyperbolic plane, there is a largest triangle. There's a triangle where all three of the vertices are at infinity. They're all on the boundary of the hyperbolic plane. And so if you can show that that triangle is slim, which it turns out to be, then all of the other triangles aren't as big. So they have to be slim as well. And that sort of largest infinite ideal triangle is not something you get in the Euclidean plane, so you can't do anything there. Of course, the Euclidean plane isn't hyperbolic. So those are some hyperbolic spaces. Now, correspondingly, let's think of some groups that act on those spaces, and so we'll get some hyperbolic groups. So first of all, finite groups. This is just boring, but finite groups are just trivially hyperbolic, and that doesn't really tell us anything interesting. Because, well, I should say, I suppose, finite groups act on, well, actually, a finite group acts geometrically on just a point. So the least interesting action imaginable, the most trivial action possible. And a point is a hyperbolic space. So finite groups are hyperbolic. Free groups. So if you draw the Cayley graph of a free group, you get a tree. And so we said trees are hyperbolic, so free groups are hyperbolic. And the group Z, this is a special case, I suppose, but the group Z acts geometrically on the real line, and that's another hyperbolic space, so Z is a hyperbolic group. And finally, our first really interesting ones, well, I shouldn't say that actually, lots of people think that free groups are very interesting, and they are in some ways, but our first really very geometrically interesting group that's hyperbolic is pi1 of any closed hyperbolic manifold. And the reason for that is if you've got a closed hyperbolic manifold, then its universal cover is the hyperbolic space of the correct dimension. And so pi1 of the manifold acts geometrically on that universal cover by deck transformations. And so pi1 of m acts on the hyperbolic space of whichever dimension, which we've said is a hyperbolic, we've said is a hyperbolic space in the sense of delta hyperbolicity. So there are some groups. One that I perhaps should have written down, another motivating reason to care about hyperbolic groups is it's a theorem that if you write down a random, sufficiently complicated presentation for a finite presentation for a group, and you can make that exactly what that means precise, but with high probability, probability tending to 1 as the complexity of the presentation tends to infinity, you'll get a hyperbolic group. So really, most groups are hyperbolic. So if you're interested in groups, then with probability 1, you're interested in hyperbolic groups. So those are some hyperbolic groups to keep in mind for the rest of the talk. Any questions about this before I move on to the ways in which splittings and boundaries are? I haven't told you about boundaries yet. I'll move on to boundaries and then I'll ask you if you have any questions. So the boundary of a hyperbolic group, first of all, we start with the boundary of a hyperbolic space. So for a hyperbolic metric space X, the Gromov boundary defined from a base point X0 is the thing that I will note. Boundary X is the set of geodesic rays that are based at this base point X0. So they start at X0 and then they go outwards. It's that up to bounded distance. So if you had two geodesic rays that somehow stayed close together forever, you quotient out by that, and you think of that as only one point in the boundary. So that's what the boundary of a hyperbolic group, the boundary of a hyperbolic space is. You might notice that I'm being a bit casual about this base point in that I'm not recording it in the notation boundary X. That's because the space is up to homeomorphism base point invariant. A different choice of base point would give you the same topological space. So the boundary it is a topological space. I suppose I've only really told you it's a set here, but hopefully it doesn't take too much imagination to think that it might be a topological space. You can sort of imagine what it means for two geodesics to be near each other. Maybe they're at only a small angle or something, and that sort of idea gives you a topology on the boundary. And then hyperbolic groups. So if you have a hyperbolic group acting geometrically on a hyperbolic space X, then we just say that the boundary of G is defined to be the boundary of X. And the reason why we can get away with that is it is secretly, if you had two different hyperbolic spaces that G acted on geometrically, then they'd have homeomorphic boundaries. So it doesn't actually matter which space we choose. So the boundary of G is the boundary of any space G acts on. Now a few examples. So, I didn't give any examples. I'll just say some examples then, maybe going back to the previous slide. So looking at our 3 examples here, finite groups, that's boring. So they act on bounded spaces, and bounded spaces don't actually contain any infinite geodesics. So the boundary of a finite group is empty. It's just the empty set. So again, finite groups are not interesting things to study from a hyperbolic group's point of view. Free groups, so the boundary of, first of all, the boundary of Z is defined to be the boundary of R, which is just 2 points, one at plus infinity and one at minus infinity. The boundary of, say, a free group on 2 generators is the boundary of the infinite tree in which every vertex has degree 4. And a fun thing to try to convince yourself of, if you haven't seen this before, is that topologically that space is a Cantor set. So maybe have a go at that if you haven't tried it before. And then third example, pi1 of m, where m is a closed hyperbolic manifold. So the boundary of that is the boundary of a hyperbolic space of the right dimension. And if you think about what hyperbolic space looks like, particularly, let's just say the hyperbolic plane, so we'll choose dimension 2. Well, people often draw this Poincare disk picture of the hyperbolic plane, where the hyperbolic plane is a sort of distorted disk. And then hopefully you can imagine that it's natural to for the boundary of that to just be the circle that's at infinity. So the boundary of H2 is just a circle. And so the boundary of pi1 of m, where m is a closed two-dimensional hyperbolic manifold, is a circle. And then similarly, in higher dimensions, the boundary of pi1 of m, where m is a closed hyperbolic n manifold, is an n-1 dimensional sphere. And then the example, yep.
May I ask something? So I may have misheard.
Yes, go ahead. Yeah.
So the Gromov boundary for a free group on two generators, that's you meant to say is separable or not countable, is it?
It's not countable, no. So these
okay.
Yeah, right. So yeah,
Okay.
it's a Cantor set. So yeah, it's an uncountable space. And did I say something completely wrong?
I may have misheard you say something.
I'm sorry. I possibly I don't know. Sometimes I just say the wrong word, so it could have been that. So yeah, I don't mean to say countable or anything. It's a Cantor set, so definitely not countable. Thanks.
Okay.
I hope I didn't say. Anyway, thank you for clearing that up. Yeah. So the example 4, random groups. The theorem about random groups tells you that, again, with high probability, as the complexity of the presentation tends to, as well as the presentations get more complicated, the boundary is going to be a Menger sponge, or sometimes people call it a Menger curve, but it's that space that you get by starting with a cube and then drilling a hole through each face and then doing that on what's left, now 8 times as many times or something. You know, it's that very famous fractal.
So, if I may, do you know when the Gromov boundary is totally disconnected? Can you
totally disconnected? Yeah, so that can actually only happen when the boundary is either 2 points, so the group is virtually cyclic, or when the boundary is a Cantor set, in which case it turns out by a big theorem of Stallings that the group has to actually be a free group. So, sorry, it has to be virtually a free group. So up to finite index subgroup, the only way the boundary can be totally disconnected is if it's free, or, well, yeah, if it's free.
Thank you.
Yeah, so occasionally, most of the time, knowing the boundary doesn't tell you very precisely what the group is, but occasionally it does. And knowing it's totally disconnected actually gives you loads of information about the group. Thanks, that's a great question.
Also, could you tell me, please, is the Gromov boundary more or less the same as the space of ends for Cayley graph of hyperbolic group, or they could be different?
They could be different. So the space of ends is the space of connected components of the Gromov boundary. So the Gromov boundary gives you a bit more information than the space of ends. Is that right? Unless I forget what the space of ends is, but I think the space of ends.
I think you are right. Yeah, like in the example 3, this group should be one-ended, but as the Gromov space is like the boundary of the hyperbolic plane or hyperbolic space.
Right, thanks, good. Yeah, so the Gromov boundary is a bit richer. It contains a bit more information than the space of ends. It sort of tells you what shape each end is, as well as just how many there are. But yeah, they are closely related, of course, because yeah, the ends do correspond to sort of connected components of the boundary in some way. Any more? I do like getting questions, so otherwise I'll move on. Okay, so this is going to be a sort of warm-up to Bowditch's theorem, but it's still a great result in its own right. So I'm first of all going to talk about splittings over finite groups. So just as an example, let's take an amalgamated product. So G is G1 amalgamated with G2 over H. Now G then is the fundamental group of a compact space Z that's obtained by gluing X1 to X2 along Y, where pi1 of Xi is Gi and pi1 of Y is H. And just as before, when we were talking about Basset theory, G acts on the universal cover of Z, which decomposes as a big graph of spaces. Here I have drawn you a graph of spaces. So this is the universal cover of the graph of spaces, of the graph of spaces decomposition of Z. So the vertex spaces are all either the universal cover of x1 or the universal cover of x2, and the edge spaces are all the universal cover of y. And I suppose there's nothing geometric in this, but it turns out that I can insist that if G is hyperbolic, I can insist that x1 and x2 also be hyperbolic and that Z be a hyperbolic space. So I might, given that I'm allowed to choose any hyperbolic space on which G acts geometrically to compute the boundary of G, I might as well choose this one. So the boundary of G is the boundary of the Gromov boundary of this space Z tilde, which is the space I've tried to draw here. I mean, it's big and infinite, so I've only drawn part of it. So just by thinking about geodesics in that picture and the fact that the boundary of y tilde is empty because y tilde is actually, I suppose I didn't say this, but because H is finite, we can choose Y to be a compact space where H is the fundamental group, and then the universal cover of Y is still compact because H is a finite group, and so Y tilde is bounded, and so the boundary of Y tilde is empty. So sort of just by imagining cutting out one of these edges, say the one I've drawn in the middle, we don't actually really remove any of the boundary by doing that, but we have separated the boundary into two pieces. So so then the boundary of G decomposes the boundary of the sort of bit on the left of this picture and the boundary of the bit on the Y of this on the right of this picture, and they don't overlap at all because the place where they would overlap is sort of in the boundary of Y tilde, but the boundary of Y tilde is empty. So hopefully this picture sort of convinces you that if G is an amalgamated product like this over a finite group, then its boundary is disconnected. So another way of saying that is that it has more than one end. In fact, we can say much more, that there's a converse to this idea, which is another famous theorem of Stallings that says that, well, yeah, the converse is true. So if the boundary is disconnected, then the group splits as a finite group. So splittings over finite groups can really be seen in the boundary. There is a splitting over a finite group if and only if the boundary is disconnected. Did I hear? Yeah.
About the previous slide. You do it in the plane, which works for a cyclic group. But if you have a finite group, is there something called the embedding dimension, or what dimension you can build this graph in?
Well, I suppose I'm not too worried about where I'm embedding the graph. The graph doesn't have to be embedded in any space or anything like that. It can just be a sort of abstract graph in its own right.
True, but has anybody asked that question of
right, of what? So the question is, what dimension of space do you need to embed a Cayley graph? Well, to embed like a presentation complex of a Cayley graph. Oh, right. Sorry, a presentation complex of a group. That's not something I know anything about. That seems like a sensible question, but I've no idea.
It can't be simple. It could be horrible, but just wondering.
Right. Anyone else? Anyone want to weigh in? Anyone know anything about that? Well, if anyone does, I mean, bring it up at the end, I suppose, or if anyone works out the answer. So Stallings' theorem is great. It tells us that splittings over finite groups can be seen in the boundary. And well, okay, I should tell you that Stallings' theorem actually says more than this, because it tells you something about non-hyperbolic, or it tells you the same thing for non-hyperbolic groups too, where we replace the boundary being disconnected with having more than one end. But just to keep in line with the theme of this talk, I'm restricting to talking about hyperbolic groups. But I don't want to sell Stallings short. Okay, so we're going to move on and now say a bit about splittings over Z. So this is the next. So if we feel we've dealt with splittings over finite groups, sort of the next simplest group is just the infinite cyclic group. So splittings over that are going to be what we're going to talk about next. And this is this Bowditch theorem that was in the title of my talk. So for simplicity, I'm going to assume for a bit that G is still going to be hyperbolic. I'm now going to assume it's torsion-free, which just makes things a bit easier. And I'm also going to assume that its boundary is connected, because if its boundary isn't connected, we just need to decompose it over some finite groups, and we'll end up with some pieces that don't decompose any further, so their boundary is going to be connected. So for any group, we can sort of cut it up into pieces with connected boundaries, so we don't really lose anything by from now on pretending that the boundary was connected all along. So that's just some simplifying assumptions for what I'm about to say. Now we're going to do exactly the same thing, and you might notice I've lazily used exactly the same picture. So suppose now that G splits over Z, now we get another action of G on a space that it looks like this, but now pi1 of y isn't finite anymore. Now pi1 of y is Z. Okay, so this changes things a bit because the boundary of this picture is no longer disconnected for the same reason, because there are sort of things with boundaries sitting on the edges, so we can't just cut along an edge and hope that that will show us that the boundary is disconnected.
May I ask another question?
Yeah.
So going back to the Stalling theorem that you mentioned.
Yeah, sure.
I mean, let me test my sanity, if I may, right? Take the free group on 2 generators, right?
Yes.
And write it as the free product of Z with Z.
Yes, great. Yeah.
How does that work, right? I mean.
Oh well, that seems to have worked, doesn't it? Because so the boundary of your free group is disconnected. It's a Cantor set, and the group splits over just the trivial subgroup. I mean, a free product is a splitting over a trivial group.
Yes.
So now we should be happy, I think, because the theorem seems to be true. That I mean, I haven't negated what I was meant to say in the theorem, have I? No. Okay. So I'm
right. So on the one hand, it should be the disjoint union, I guess, of each one of the pieces.
No. Right. Yeah. Yeah. You might think that. Yes, I think I definitely used to think that. I mean, when I look, I definitely thought that once. That's not the case. Yeah. So
okay.
In fact, you don't get the boundary of the free product isn't just like a union of the boundaries of the two pieces, and I can tell you why. Going back to this picture here.
Yes.
If we look at this graph, there are loads of different copies of x1 and x2 in this picture.
Okay.
We get like 2 points for each of these pieces, and then actually you get some more points as well. But yeah, so
I see.
The picture we see things are much more complicated than
I see. Thanks for clarifying this.
No, thanks. That's a really great question. That's yeah. Thanks for asking. Okay, so getting back to this. So now we're in the same sort of case, except now our edge groups have infinite cyclic fundamental group rather than finite fundamental group. But if we imagine removing the boundary of one of these edge groups, that will still disconnect the thing for the same reason. We'll get the boundary of the left part and the boundary of the right part. And now the boundary of one of these edge pieces is just 2 points. So what I hope I've sort of convinced you of is that the boundary of the group, so the boundary of the original group was connected, but you can disconnect it just by removing 2 points. Okay, so like a circle you can disconnect by removing 2 points, but a sphere you can't disconnect by removing 2 points. So what I have aimed to justify here is a claim that if a group splits over Z, then its boundary contains what's called a cut pair, so a pair of points, so that if you remove those points, you've disconnected the boundary. Okay, and then Bowditch's theorem, just like Stallings' theorem, or just like for splittings over finite groups, I gave a simple argument in one direction, then quoted a big theorem in the other direction. I'm doing the same. So Bowditch's theorem is the converse of what I just said. So if G is under those assumptions, G splits over a cyclic group, an infinite cyclic group, if and only if the boundary contains a cut pair. I would stress that this is only true in the torsion-free case. So I do need to say this disclaimer, so I'm not misleading you. This is a theorem very much. So on the next slide, I'm going to tell you a bit about where things change for torsion. I just don't want to lie to you. So yeah, I'm just going to stress torsion-free. Then we get that G splits over Z if and only if the boundary contains a cut pair. Any questions about this before I say something quick about torsion?
Maybe just to make sure. So a cut pair is just a pair of points on the boundary that disconnect the boundary?
Yeah, that's exactly it. So a cut pair is a pair of points in the boundary whose complement is disconnected, you could say.
Okay.
Can I think of that cut pair as the geodesic as a ray going through all of those covers you do on the last slide?
Yeah, right. Yeah, perfect. Yes. So the cut, exactly. Yeah. So
And so that means there's an uncountable number of cut pairs because you take any ray like that.
Yes. I mean, well, not an uncountable number, I suppose. Well, I suppose not all of those rays are actually going to disconnect. So
Okay.
maybe things are actually slightly different, actually. So yes, any ray in this picture, or any, sorry, bi-infinite geodesic will give you one point at each end. But I think you need to think a little bit harder about the topology in order to decide which of those are going to be actually cut pairs. So yeah, you can see pairs of points in the boundary like that, and then with some thought, you can decide which ones are actually cut pairs.
Okay, thanks.
I have another question, which is so here you have, I mean, in the previous slide, you have this subgroup Z. It has like 2 points on its boundary, but then as a subgroup, under what conditions do we know that the boundary of the subgroup can actually contribute to some points on the boundary of the larger group?
That's a great question. Yeah, thanks. So it'd be nice if whenever you had a subgroup, the boundary of that subgroup was a subspace of the boundary of the whole group. That isn't always true. The condition that I'm not really talking about today, but you should look up if you're interested, is that you need the subgroup to be a quasi-convex subgroup, and then that's the case. And it turns out that whenever Z is a subgroup of a hyperbolic group, it's quasi-convex. So Z is very special like that. Z is always quasi-convex.
Okay.
That turns out to be true. And then actually there's loads of nice theory about when the boundary, sorry, when the subgroup isn't quasi-convex, maybe the boundary of the subgroup isn't a subspace anymore, but maybe it sort of maps in a natural way into the boundary of the whole group. But anyway, sorry, that's getting off topic. But yeah, that's a nice sort of thing to think about, what the boundaries of subgroups look like in the boundary of the whole group.
Can I ask if the group splits over a subgroup, is that subgroup always quasi-convex?
I don't think it has to be. Let's see. Do I know an example? Ah, yeah. So I know quite a technical example, which isn't going to really appeal unless you know quite a bit about hyperbolic 3 manifolds. But I'll say something. So if you have a hyperbolic 3 manifold that fibers over the circle, then then sort of one of the surface fibers cutting along that decomposes the group as splits the group over a surface group, but those surface pieces actually don't have to be quasi-convex. So yeah, that's in fact I think the only example I know of.
Thanks.
The only example I can describe where that goes wrong. Okay, so I don't have very much more to say, which is great because I've only got 5 minutes. So I'm just going to say something quick now about what goes wrong with torsion and, well, the fact that in fact you still can rescue this. So in the presence of torsion, the ideas still work. Now you need to replace splittings over Z with splittings over any virtually cyclic group, so any group that has Z as a finite index subgroup. That's not such a big problem. The bigger problem, I suppose, is now Bowditch's theorem has an infinite number of exceptions, but so there are actually hyperbolic groups that have cut pairs in their boundaries that don't split over virtually cyclic groups, but happily you can sort of write down what all of them are. They're all the so-called triangle groups, which here's an example of one of these. Here's a presentation, which maybe looks a little bit complicated. It's generated by A, B, and C, with A squared, B squared, and C squared all being the identity, and AB squared, BC cubed, and CA to the 7 all being the identity. What's that got to do with triangles? Well, here's a tiling of the hyperbolic plane by triangles, black and white triangles. And this group is actually the symmetry group of this tiling. So choose any one of the triangles you like, then call the reflections in each of the edges of that triangle A, B, and C, and then with some quite difficult geometric thought, you can maybe convince yourself that this group, that then those generate, well, first of all, I suppose that those reflections generate the whole symmetry group of the tiling, and secondly, that then the symmetry group of the tiling has this presentation that I've written down. Okay, so what goes wrong? So this group acts on the hyperbolic plane because this is a tiling with the hyperbolic plane. So its boundary is a circle. Circles definitely contain cut pairs, but this group sadly doesn't split over Z or indeed over anything. This group has a special property called Sayre's property FA, which says that whenever this group acts on a tree, it fixes a point. So really there aren't any interesting groups of actions of this group on trees. So I'm just putting that out there just to warn you off trying to think that the theorem holds for groups with torsion as well. So that's really everything I wanted to say, but I just want to make one final comment so that just about Bowditch's theorem. I've stated something fairly simple here, that having a cut pair in your boundary is equivalent to splitting over Z, or whatever for the torsion case. Bowditch's theorem is actually much better than that, but it's quite technical, so I haven't completely done it justice here. So Bowditch's theorem actually tells you that you can sort of read the whole structure of splittings over virtually cyclic groups just off the sort of structure of cut pairs in the boundary in a way that I'm not going to tell you because it would take quite a long time, but it's actually really neat and really quite attractive. So it's nice, but sadly no time for that. So that's everything I was going to say. So thank you very much for all of the questions during the talk, and yeah, I'm happy to take any more questions now.
Yes, thanks, Ben.
I have a
Are there any
question
questions? Yeah, go ahead.
regarding a comment that Stephen made with regards to the number of cut points. If I recall correctly, the action of G on the Gromov boundary should be minimal, right? Is that correct?
Yeah, that's right.
And so that means you would be able to take cut points and then just move them around using this symmetry. Is that right?
That's true. So yeah, there's always going to be infinitely many. So if there are any cut pairs, then you can sort of move them around.
Well, that would give you a countable number, though.
Yeah, right. That you only get a countable number like that.
And then the question
I
is
see.
the irrational limits sometimes are special because you keep doing irrational moves, and it's an action of the closure of the group.
Yeah. I don't know. Yes, I think those two correspond to interesting things. It turns out that sort of you get sort of these. I'm now saying something a bit technical that I don't really know how to say exactly, but this theorem of Bowditch, the full version, sort of tells you that you sometimes have like cycles of cut pairs in the boundary, and those correspond to surface pieces in the group. And then like the irrational points in those cycles correspond to laminations of the corresponding surfaces. So there's something neat going on in the background there anyway.
I see. Okay.
Is every cut pair kind of fit into that description somehow?
Almost, yes. So all cut pairs come from splittings, except the cut pairs that come from that are in surfaces. Because so a surface piece has a circular boundary, and well, that has uncountably many cut pairs, so they can't all come from splittings because there are only countably many subgroups to split over. So definitely only countably many splittings. So yeah, when there are like surface pieces, then not all of the cut pairs correspond to splittings in a sort of nice one-to-one basis, but that's the only thing that can go wrong. All other cut pairs come from splittings.
Are you saying that, at least in the case of surfaces, you take a pair of points or even cut pair it's not necessarily true that there is a cyclic subgroup where the boundary are exactly the 2 points.
Yeah, that's right. And
But
that
then is that true for like groups of higher dimension? Is that what's going wrong in the surface group case, or?
So I suppose it'll always be the case that like there are pairs of points that that aren't the boundary of some infinite cyclic subgroup, because there only can be many infinite cyclic subgroups. So that goes wrong there. But what I'm saying, I suppose, is imagine that your group doesn't contain any surface pieces, and there's a way to make that precise. Then whenever you have a cut pair, that actually is the boundary of an infinite cyclic subgroup, and the group splits over that infinite cyclic subgroup.
Cool. Yeah. Thanks.
So surfaces are the thing that's ruining everything, just as they are with this sort of triangle groups issue.
Okay.
If you wanted to, instead of like excluding triangle groups specifically or like excluding torsion specifically, could you get something like this to work if you only cared about having the splitting virtually?
I think so, yes. Well, yeah, I guess you could. Yeah, because I suppose all of these. Oh, could you? So I guess what I want to do is say that what I want to say is whenever you have one of these weird sort of triangle-y things, you should be able to pass through a finite index subgroup so that your group is now just a normal surface group. So it does admit a splitting. So now things are fixed. But is there an issue with hyperbolic groups not necessarily being residually finite? I guess it's okay, actually, because it's only surfaces you're really thinking about here. You're only thinking about like things that act on the hyperbolic plane. So yeah, I think you can do that.
Okay. If there are no further questions, is there another question?
I almost made a quick comment. I will just make a very quick comment that if you want to keep reading about this sort of thing, there's lots in the literature about applying similar ideas to groups that aren't hyperbolic as well, like relatively hyperbolic groups, or you can even prove much weaker things about things like finitely presented groups. That's a theorem by Panos Papasoglou and possibly someone else, which is very nice and in that direction. But that's just a sort of advertisement.
Okay.
Can I ask? Sorry, can I ask one more
Yeah,
question?
go ahead. Yeah, sure.
If you have is there any higher dimensional analog of this? Like if you have a circle in the boundary that disconnects the boundary, could you split it over a surface group or something like that?
That's a natural question, isn't it? And it would be nice, but I'm pretty sure the answer is the answer is no. I don't quite know why the answer is no, but it definitely is. Let's see.
Actually, you could probably prove the Cannon conjecture if you.
Exactly. That's one reason why the answer is no.
But it sounds like it should be true, right?
It does, yeah. But yeah, I guess just because we haven't proved the Cannon conjecture, we know that. I think if we knew that groups that had the two sphere as boundary, if we knew that they all had lots of surface subgroups, which this would tell you, among other things, then yeah, as you say, we'd have proved the Cannon conjecture. So yeah, I mean, it does seem like you should be able to, but.
Sorry, as I was asking the question, I realized that I already knew. Yeah, but anyway.
No, thanks. Yeah, thanks.
Cool. Thank you.
All right. I guess now let's thank Ben again, and he'll give another talk next week at the same time.
Well, thank you very much for the invitation, and I'm sorry, no jokes.
Thank you.
Great talk. Thank you.
Thank you for your talk.
I guess I'll stop sharing my screen.
Thanks. Bye.
Thanks.
I'll see you next week then.
Yeah, see you next week. Bye then.